Hello, my awesome AP Chemers. So last time we talked about the three different types of reactions: redox, precipitation, and neutralization that you need to recognize on the AP exam. Today we're going to talk more about redox reactions, since most reactions are redox. And redox reactions are where electrons are transferred. One or more electrons are transferred. So to recognize that it's a redox reaction, you need to assign oxidation states for each of your elements on both sides and see if any of them have changed, and that tells you that a redox reaction occurred. So let's look over the rules for assigning oxidation states. So the first rule says that the oxidation state of an atom in an element in its natural free state is 0. So for example, let's say you see just Na by itself, then its oxidation state is 0. Or you see O2 by itself, that's oxidation state of 0, because the natural free state of oxygen is O2. So those would be an oxidation state of 0. Next, it says oxidation states of monoatomic ion is the same as its charge. So if you see an Na plus, then the oxidation state of that is +1. If you see an O with a 2 minus, then the oxidation state is -2. Just a little side note here. For some reason, when we write the charge of an ion, on the ion itself, we usually write the number and then the sign, so 2 minus or 2 plus, something like that. But when we write the oxidation number or oxidation state, we usually write the sign first and then the number. Now, if you do it the opposite for either one, it wouldn't matter. They would accept both, but that's just traditionally how we write it. The next rule says the oxidation state of oxygen in compounds is -2, except when it's in a peroxide, then it's -1. So for example, let's say I have water, H2O. Then in this case, the oxidation state of that oxygen is -2. However, if I have a peroxide, and usually the most common peroxide that we know of is H2O2, then in this case, the oxidation state of this oxygen is just -1. And just so you know, the AP exam is not big on exceptions. They care more that you know the general rules, so I wouldn't spend a lot of time, figuring out is it a peroxide or not. I think if you know that this is hydrogen peroxide, you're good with this. Okay, next, it says the oxidation state of fluorine in compounds is -1. So let's say I have CuF, then the fluorine in this case is -1. Whereas if it was F2, it would be 0 because that's an element in its natural form. Next it says the oxidation state of hydrogen is +1 in compounds with nonmetals, and it is -1 in hydrides. Hydride means you have a metal bonded to hydrogen. So for example, back in the water example, hydrogen here is in a compound, and so it would be, +1. However, if it's a hydride like LiH, then in this case, because the lithium has to be a +1, in this case, the hydrogen is -1. So when it's in a compound with nonmetals, hydrogen is +1, like in water. But when it's in a hydride, like a metal bonded to the hydrogen, then it is -1. And then next it says the sum of the oxidation states in a compound must equal to 0. So let's look at one of the compounds that we made, LiH. So hydrogen here is -1, lithium is +1, so they total to 0. Let's look at water here. So each of the hydrogens is +1 for a total of +2. The oxygen is -2, so +2 and -2, that equals 0. And then the last 1 here, it says the sum of the oxidation states in a polyatomic ion must equal its charge. So that means that if I have, let's say, NO3 minus, that's a polyatomic ion, that's nitrate. If I add up the oxidation state of this nitrogen and the oxidation states of each of those 3 oxygens all together, if I add them up, they should equal to -1, or whatever the charge is on the polyatomic ion. So let's practice figuring out what the oxidation state of these elements are in these substances. So for Li2O, we don't see any rule about lithium here, but we do see a rule about oxygen. It says in compounds it's -2. So the oxygen we know is -2, which makes the lithium +1. We also know that this is an ionic substance, and so it's really made up of Li pluses and O2 minuses, so that's another way that you can figure it out. If it's ionic, then it's going to be whatever the charge is on the monoatomic ion, like rule number 2 says. Okay, let's do the next one. We have H's, we have P's, and we have O's. So we have a rule for hydrogen. The rule for hydrogen says that it's +1 in compounds, so it's +1. We don't have a rule for phosphorus, so we'll skip it. We do have a rule for oxygen. It says that it's -2. So then we need to figure out what phosphorus is. So you can do it in your head, or you can write out an equation if you want. So I'm going to write it out just so you can see my thinking here. So I have 3 of the hydrogens, and each of them is +1. Then I have the phosphorus, and I just have 1 of these phosphoruses, so I'm going to call it X. And then I have 4 of the oxygens, and each oxygen is -2. All of this together needs to equal to 0 because it's a neutral compound. So then I solve for what X is. And so that ends up being +5. Okay, let's look at permanganate. So we have manganese and we have oxygen. We know oxygen is -2 from the rule here, but we don't have a rule for the manganese. So what you would do, let me do it in a different color here, easier to see. So you'd say my manganese is my X, and I have 4 of these oxygens that are each -2, but all together they need to equal to -1, whatever the charge is. This was 0 because it didn't have a charge. This is -1 because it does have a charge. And so in this case, the manganese needs to be +7. Okay, last one, the dichromate. We don't have a rule for chromium, but we do have a rule for oxygen. Oxygen is -2 in this case. The chromium, you'd say, I have 2 chromiums, so 2X, because each X is a chromium, plus 7 of these oxygens that are each -2. All together, that needs to equal to -2. And you solve for X, so in this case, X is +6. Okay, so that's how you assign the oxidation states, also known as oxidation numbers. So what is a redox reaction? A redox reaction is a reaction where electrons are transferred. And so that means one substance gives away the electrons, the other one gains those electrons. Loses electrons, the other gains them. So they are transferred from one to the other. So redox stands for reduction and oxidation, or oxidation and reduction. Do you guys remember Leo goes Gur? Leo, the lion, goes Gur. So this stands for loss of electrons is oxidation, gain of electrons is reduction. Some people prefer oil rig. This stands for oxidation is loss of electrons. Reduction is gain of electrons. So oxidation means that you are losing electrons. That's the LEU. Reduction means electrons are gained. Now, I think reduction is much better named than oxidation, because oxidation you think like you're adding oxygens, which is not really always the case with oxidation, but reduction I think is a good name for it, because when we are talking about reduction, the charge is reduced. And this is actually how I think about it. I think reduction means charge is reduced, and so the charge is going down. So then what happens with electrons? Electrons are negatively charged, and so if I gain electrons, my charge will go down. Whereas in oxidation, charge is increased. Because if I lose electrons and those electrons are negative, if I lose the negative, I become more positive and my charge goes up. Oxidizing agent and reducing agent, that language is out of the AP exam, so they will never ask you what is the oxidizing agent or what is the reducing agent. I, again, have this in your notes just so that you have them for when you go to college. That's something that you need to know. So it is, an oxidizing agent is kind of similar to like a real estate agent or a travel agent. They themselves don't do these things. So for example, a real estate agent helps me buy a house. They themselves don't necessarily buy that house. Or a travel agent helps me travel. They themselves don't necessarily travel. So an oxidizing agent does not get oxidized. It causes something else to be oxidized. So oxidizing agent means it causes another substance to be oxidized. So what does that mean? It causes something else to lose electrons. Right? Well, how is it going to cause something else to lose electrons? That's because it itself gains those electrons and gets reduced. So it itself gets reduced, or it gains electrons. So if it's hungry for electrons, it wants to gain those electrons, it's going to cause something else to lose those electrons. So it gets reduced, and so it's an oxidizing agent. It causes something else to be oxidized. So similarly, a reducing agent is something that causes another substance to be reduced. Which means it causes that substance to gain electrons. And so how does it do that? Because it loses electrons, it gets oxidized, so it forces something else to gain those electrons that it doesn't want. So it itself gets oxidized, which means it loses electrons. So again, this part is not on the EP exam. This is just for your notes. So when you take your notes, you might want to write that down on the side. I mean, I have this here for you, but don't worry about studying that for the test or for the AP exam or anything like that. This is just for your own notes. All right, so let's look at a redox reaction. So we have magnesium reacting with nitrogen to form Mg2 plus and N3 minus. So let's figure out if this is a redox reaction. I mean, obviously, if it's here, it's probably a redox reaction, but let's figure out how you would know that on the AP exam. So what you would do is you would look at each of these elements that you have. So we have magnesium and nitrogen, and assign the oxidation states for each of them. So this magnesium is 0. This nitrogen is 0, because those are elements in their natural state. This Mg2 plus is obviously plus 2 because it's a monoatomic ion, so it has a charge, so that charge is its oxidation state. And then this nitrogen has a minus 3 here. Okay, and so we look at the magnesium going from 0 to plus 2, the nitrogen going from 0 to minus 3. So I always ask myself, because again, reduction is better named than oxidation, so I always ask myself, which one was reduced? Again, reduction means you're getting electrons, which means your charge is reduced. So which one is reduced? Which one its charge went down? Well, it looks like the nitrogen went from 0 to negative 3. Negative 3 is lower than 0, right? So the nitrogen got reduced. So if you wanted to write the reduction reaction, you just write the one with the nitrogen. So N2 going to N3 minus. Okay, now let's balance it. We need 2 nitrogens, right? And then how would we balance the charge? Do you remember? We add electrons, right? So here the total charge is 0. Here the total charge is minus 6, right? Because there's 2 nitrogens, each is minus 3. So I need 6 electrons on this side. Look at that. It gained electrons. And so its charge went down, got reduced. Okay, let's look at the oxidation reaction. So that must be the one with magnesium, right? Because we did nitrogen already. So magnesium went from 0 to plus 2. Its charge did not go down. Its charge increased. It went up from 0 to plus 2. And so the oxidation half reaction is Mg going to Mg2 plus. Let's balance it. My magnesiums, I have 1 and 1. My charge, though, is not balanced. This is neutral. This is plus 2. I can only balance with electrons, so I need to add my electrons here. I need 2 electrons there. So the magnesium lost, each magnesium lost 2 electrons, and the nitrogen gained, each nitrogen gained 3 electrons. So if I wanted to balance this whole thing, I'd need to multiply this by 3 so that I would lose a total of 6 electrons. Excuse me. And your nitrogens would gain a total of 6 electrons. We'll do that in a minute where we balance, so don't worry about that yet. That was just kind of like a side note here. If you wanted to know what the oxidizing agent and what the reducing agent is, you'd say, well, the nitrogen got reduced, so that means it's the oxidizing agent. It gained electrons, so it forced something else to lose the electrons. The magnesium got oxidized, and so that means it's the reducing agent. It caused something else to be reduced. Again, that's not an AP exam, but I want you to be aware of that so that when you go to college, you did not miss on that. All right, so if you remember last year, we balanced redox reactions, so we're going to do that again. We are going to do all of these steps, but the hard part of it, I think, was maybe step 4, and you do not need to be able to do step 4 for the AP exam. We're going to do it in our notes, and I think I assigned you a few on the homework, just so you understand what's going on. But on the AP exam, they will not ask you to balance the hydrogens and the oxygens and all that. They will be asking you to be able to do any of the other steps, though. So the ones that don't have oxygens and hydrogens, you need to be able to do. So let's go through and do these steps for those 2 reactions here. So this one, they're telling us it's in an acidic solution. So I'm going to be going back and forth. Step 1 says identify the oxidation numbers of all species, then decide which ones have changed. That's something that you need to be able to do. Now, if you remember from last year, you don't actually have to be able to do that to balance them. This is just so that you can tell which one was oxidized, which one was reduced, but it's not really something that you have to know how to do. So let's do it just for fun. This oxygen I know is minus 2, right, from my rules. The manganese, so if I take 1 manganese and 4 of these, so negative 8, the total needs to be negative 1, right? So that means the manganese is plus 7 in this case. Let's look at this here, oxalic acid. I know that this is -2 because it's oxygen. I know that the hydrogen is +1. And so I need to figure out what the carbon is. What do you think? That's a +3 for this carbon. Okay? The manganese on the other side, it's a monoatomic ion. It has a charge, so it does +2. That one's easy. Carbon dioxide, this oxygen is -2. So what does that make? The carbon here, +4. So it looks like the manganese got reduced, went from +7 to +2, went down. And which one got oxidized? The carbon went from +3 to +4. The oxygens, they remained the same, and hydrogens disappeared. You'll see why in a minute, how that happened once we balance it. Again, you do not need to be able to do that step to balance it, but we wanted to practice it because it's something that you need to be able to do, assign oxidation states and figure out what oxidized, what was reduced. All right, step number 2 says split the reaction into the oxidation and reduction half reactions. You could have done that without assigning any oxidation states because you should be able to tell that the MnO4- should go with the one that has the manganese, the Mn2+, and the oxalic acid should go with the one that has the carbon, the CO2. We don't worry too much about the oxygens and the hydrogens because they work themselves out. All right, we got that part. Next, balance all atoms that are not oxygen or hydrogen first. So let's do that. Yep. One manganese, 2 carbons, just 1 carbon, so we need to make that a 2. Step 4. That's the step that's kind of complicated, but you don't really have to be able to do it except for just for the homework. So it says, 4a, balance each oxygen by adding 1 water to the deficient side. So let's go back and look. 4 oxygens here, none there, so we need 4 H2Os. On this side we have 4 oxygens. Here we have 2 times 2, which is 4 oxygens, so that side is good with the oxygens. Next step. Balance each hydrogen by adding 1 H+ to the deficient side. So, hydrogens, I have none here, I have 8 here, so I need to add 8 H+ on this side. For this one, I have 2 hydrogens here, none there, so I need to add 2 H+ on this. Now, where are we getting these H+ and waters? How are we just like randomly creating matter and adding waters and H+? Well, we're not really creating matter. Obviously, we can't, right? This is telling us this reaction is happening in an acidic solution. So if it's in a solution, that means there's water around that can participate in the reaction. And if it's an acidic solution, that means that you have extra H+ in that solution that can also participate in the reaction. So that is why it is okay to add these H+ and these waters in here, because this reaction is happening in an acidic solution where H+ and waters are around that can participate. Okay, so that was step 4. Step 5, balance the charge by adding electrons. So how do we do that? So what I like to do is I like to kind of check what the charges are on all the sides. So here I have a +8, right? +1 times 8 is +8. Here I have a -1. So my total on this side is +7. Here I have a +2. Water's neutral, so my total is, I'm out of space here, +2. Okay, so I'm comparing the +2 to my +7. So I need to add electrons to balance. Electrons are negatively charged. All they can do is make the charge go down, right? Because they're negative. So you always want to add your electrons to the more positive side. So you have a +7 and a +2. The more positive side is this one, so I need to add electrons to this side. So how many electrons do I need to add to the plus 7 to make it equal to plus 2? That would be 5 electrons. So I add 5 electrons here. Okay, let's look at the other one here. Do the same thing. So this is neutral, just 0. This is neutral. This is a plus 2 for a total of plus 2. So I need to add electrons, and I always add my electrons to the more positive side. So this is neutral, this is plus 2, so plus 2 is a higher positive. So I add my electrons on this side. How many electrons do I need to add to the plus 2 to make it equal to 0? I need to add 2 electrons. If you do this correctly, on one side you add the electrons to the reactants, on the other side you add the electrons to the products, because one of them is losing the electrons, the other one gains the electrons. Which takes us to the next step, step 6. If necessary, multiply one or both balance half reactions by an integer to equalize the number of electrons transferred in the two half reactions. What does that mean? Well, since we're saying that one is losing the electrons and the other one's gaining them, since those electrons are being transferred from one to the other, they have to be the same number of electrons, right? One loses a certain number, the other one gains that certain number. And so we can't have those numbers of electrons be different. So what you want to do is multiply both reactions, or just one, by an integer to make the electrons equal. So I have 2 and I have 5. I need to make those equal. So I have to multiply both sides. I multiply this one by 2 and this one by 5. So I'm going to rewrite it multiplied by 2. So that would be 16H plus 10 electrons plus 2 MnO4 minus yields 2. Oops, I'm sorry. Oh, we're good. 2Mn2 plus 8H2O. Okay, on the other side I'm going to multiply by 5, so I'm going to say 5H2C2O4 yields 10 CO2 plus 10 H plus 10 electrons. All right, let's go to the next step, step 7. Add the two reactions together and cancel any like terms on both sides of the equation. So we split them up into two equations. Now it's time to put them back in one equation. So that means you take all your reactants, add them together, and then draw an arrow, and then you do all of your products on the other side. So I'm going to do that. 16H plus 10 electrons plus 2 MnO4 minus plus 5H2C2O4 yields, and then my products, 2 Mn2 plus 8H2O plus 10 CO2 plus 10 H plus 10 electrons. We want to cancel anything that we see is the same on both sides. If you did this right, your electrons should always cancel, because same number of electrons lost equals the same number of electrons gained. So I should be able to cancel my 10 electrons. Do you see anything else that's the same? Sometimes you won't, sometimes you will. In this case, I see some H pluses on both sides. So I see 16 on this side and I see 10 on this side, so I can cancel out 10 of them with 10 of these, and so I'd have 6 left over. I don't see anything else, so I'll rewrite it. 6H plus 2 MnO4 minus plus 5H2C2O4 yields 2 Mn2 plus 8H2O plus 10 CO2. All right, step 8, if basic. Well, it's not basic, it's acidic. Skip it. We don't need to do that part. The last step, check to make sure mass and charge are balanced. So normally when you balance regular equations, you check that all your atoms are the same number. So I'm going to make a list here. So I have hydrogens, I have manganeses, I have oxygens, I have carbons. That's, I think, the whole thing. And then I also check the charge. So let's check hydrogens first. 6 and 10 is 16. On this side, 8 times 2 is 16. That checks. Manganeses, 2 and 2. Oxygens, 2 times 4 is 8, plus 5 times 4 is 20, so 28 altogether. On this side I have 8, and here 10 times 2 is 20, so 28 altogether. Carbons, 5 times 2 is 10, 10. So my mass checks. Let's check the charge. So here it's a plus 6 minus 2, 0 for a total of plus 4. On this side I have plus 4, neutral, neutral for a total of plus 4. So that checks. So that means this is my balanced reaction. You feel so accomplished when you get it done. Again, the ones on the AP exam will not involve hydrogens or oxygens, which makes it much, much simpler. Okay, let's try this one. This is a fun one. It's a basic one. So first we want to assign oxidation states and figure out what was oxidized and what was reduced. Again, you do not need to be able to do that in order to balance it, but we'll do it because it's a skill that we need to know how to do. So here my oxygen is negative 2, my hydrogen is plus 1, and that makes my bismuth plus 3. Another way to do this is you can say 1 OH is a hydroxide, so it's minus 1, and there's 3 of them, so that makes the bismuth plus 3. This one, the oxygen is negative 2, which makes the tin plus 2, to make it all equal to negative 2. Bismuth here is a neutral element in its natural state, so it's 0. My oxygen is negative 2, which makes my tin plus 6, to make it all neutral. So, looks like the bismuth went from plus 3 to 0, that got reduced. And my tin went from plus 2 to plus 6, which got oxidized. The oxygen remained the same. Hydrogen, we'll see that it will remain the same. So my next step is to split it up into the two half reactions. So I know that EiOH3 is going to go with bismuth. That's my reduction. And the SnO2 2- is going to go with the SnO3. Next, I'm going to balance all atoms that are not oxygen or hydrogen. So 1 bismuth, 1 bismuth, 1 tin, 1 tin. That one's good. Next, I balance my oxygens and my hydrogens. First, I do the oxygens by adding water. So there are 3 oxygens, none here. So I will add 3 H2O. Here I have 2 and 3, so I need just 1 H2O. My next step, 4B, is to balance the hydrogens by adding H pluses. So here I have 3 hydrogens, here I have 6, so I need to add 3 more on this side. Here I have 2 hydrogens, none there, so I'm going to add 2 on this side. Next step, step 5, is balance your charge by adding electrons. And that's one of the trickier steps, I think. So this is a plus 3. This is neutral for a total of plus 3. This is neutral, neutral, total is 0. So I add my electrons to the more positive side, which would be this one. And how many electrons do I need to add to the plus 3 to make it equal to 0? Yep, that would be 3 electrons. Okay, let's do the same thing on the other side. My water is neutral. This is negative 2 for a total of negative 2. This is neutral. This is plus 2 for a total of plus 2. So you add your electrons to the more positive side. And that would be this one. How many electrons do I need to add to plus 2 to make it minus 2? That would be 4 electrons. If we did it correctly, one should gain the electrons, one should lose the electrons. Okay, my next step, step 6, is to make the number of electrons the same. So how do I do that? I have 3 electrons here, 4 electrons there. So I would need to multiply this by 4 and this one by 3. And I'll rewrite that. Nice different color. All right, so we have 12 electrons plus 12H plus 4 BiOH3 yields 4 Bi plus 12 H2O. On this side, I have 3 H2O plus 3 SNO2 2 minus yields 3 SNO3 plus 6 H pluses plus 12 electrons. The next step, step 7, says combine both reactions together to make it into one and cancel any like terms. So I'm going to put all my reactants on one side, then an arrow, and then put all my products on the other side. So I'm going to say 12 electrons plus 12H plus 4 BiOH3 plus 3 H2O plus 3 SNO2 2 minus yields 4 Bi plus 12 H2O plus 3 SNO3 plus 6 H plus 12 electrons. All right, any like terms? We see electrons, 12 electrons, 12 electrons. The H pluses, we have 12 here, 6 there, so we can cancel those 6, and we'd end up with 6 here. Waters, we have 3 waters here, and 12 here, so we can cancel those 3, and have 9 left. All right, let's rewrite that so it looks a little bit neater. So 6H plus 4 BiOH3 plus 3 SNO2 2 minus yields 4 Bi plus 9 H2O plus 3 SNO3. All right. Step 8. If basic. Ooh, this one's basic. We know that because it tells us that it's basic. It says basic solution right here. So let's read this one together. If basic, add 1 OH minus to both sides of the reaction for each H plus. So for each H plus, we're going to add an OH minus, but we're going to add it to both sides. So let's go back. We have 6 H pluses here. So that means we're going to add 6 OH minuses. 6 OH minus. Problem is, we just spent, at least 5 minutes trying to balance this, and it should theoretically be balanced, right? But if I just add the 6 OH minuses, now I messed up my atoms, my oxygens and my hydrogens, and I messed up my charge as well. So what do? Well, I got to add it to both sides of the equation. So if I added 6 OH minuses here, I add 6 OH minuses. Now, why is it that I want to get rid of those H pluses? Why is it that I'm adding OH minuses to the H pluses? Well, because if this is a basic solution, we don't have extra H pluses swimming around. We have extra OH minuses swimming around. So we can't have really something that's acidic sitting there in a basic solution. It's not really going to happen. So that's why we add that. Now, once we do that, the OH minuses and the H pluses combine to make water. So this combines to make 6 H2O. Sometimes, you're done. Other times, you might have some water on the other side or on the same side. So you gotta fix the waters. There's 6 waters here now. There's 9 here, so I can cancel those 6 waters with 6 of these to make it 3. Now let's rewrite it, and it should be hopefully good. So 4 BiOH3 plus 3 SNO2 2 minus yields 4 Bi plus 3 H2O plus 3 SNO3 plus 6 OH minus. Let's check that it's correct. Let's make a list. We have bismuth, we have oxygen, we have hydrogen, we have tin, and then we want to check the charge as well. All right, bismuth, 4 and 4 checks. Oxygens, there's lots of those there. So 4 times 3 is 12 plus 6, so 18. On this side we have 3 plus 9 is 12 plus 6, 18. Good. Hydrogens. 4 times 3 is 12. On this side we have 3 times 2 is 6, and another 6, so that's 12. 10. 3 and 3. Good. Now the charge. This is neutral. This is -2, but there's 3 of them, so -6 for a total of -6. Here, neutral, 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 -6 for a total of -6. Look at that. We did it.